We will only do 30 minutes at a time. As I explained to people when I started this, I'm going to have to run downstairs and dump this on my computer like halfway through the review today. Because I don't have a very big memory card. I'm working on it. Next semester, I'm going to be just like Superman online, YouTubing everything. It's going to be awesome. But I'm not quite there yet. I got this idea too late. Anyway, so this is 5x minus 5z, and this is 10x minus 10z. Doesn't that just mean that x and z have to be equal? Yeah. So t, t. And my basis is just 1, 0, 1. Does everybody see that without having to go through a huge amount of work? You could, of course, get that by doing EROs, but you can get it so much faster. All right, so those are the bases for the different eigenspaces. So if I asked you, I guess we didn't ask this question, but if I did ask you to find the matrix S and D, it's very easy to do that now. You just grab the vectors, because it is diagonalizable. I grab the vectors that I have found. So I can put them in whatever order I want. Let me just put 1, 0, 1 right there, and then 1/2, 0, 1 right there, and then -1/2, 1, and 0 right there. And then the only requirement that you have to be careful about when you write down the diagonal matrix, make sure that the lambdas are in the corresponding columns. So we put the eigenvalue, or the eigenvector corresponding to lambda equals 4 in the first column, so I've got to put a 4 there. And then the other eigenvalues are going to go in the other two columns. You can leave your matrix blank if you want. Anything that's blank is assumed to be a 0. Okay, so that's basically the diagonal matrix. Is this making any sense at all? Okay. Let me just follow up with one more follow-up to all of this on the same problem. Let's suppose we had a system of differential equations that had that coefficient matrix, right? So see, I can ask you like a whole bunch of questions just based around this one matrix. So the follow-up question right now, the follow-up would be find the general solution. Find the general solution to x prime equals ax. This is the stuff we were just learning this past week or so. Okay, so we can find this general solution very easily now. Because if you remember, the solutions to this system, they all take the form e to the lambda t times v. And the lambda is the eigenvalue and the v is the eigenvector. And we've already found all those things. So we actually can go straight to the answer. Okay, so the answer in this case is it's going to be, what's the dimension of the solution space going to be? 3. It's a 3 by 3 matrix. So it's a 3-dimensional solution. So I'm expecting 3 terms down here, right? 3 terms. The first term will start off with C1 times what? E to the 4t, we'll use, it doesn't matter which one you do first, we'll do e to the 4t times what? 101, very good. So C1 e to the 4t times 101 plus, what's the next term? C2 e to the negative t times? 1/2, 0, and 1. Plus C3. Okay, this gives me a good opportunity to say a quick word here. Back in chapter 6, when we had a repeated eigenvalue and we were writing down the general solution, you remember that in order to make our solutions linearly independent, we had to stack some x's in front. So for example, if e to the negative x was a solution, then our next solution with the same root would have been x e to the negative x. Okay. We actually don't need to stack a t in front of this, even though we are repeating the same eigenvalue. And the reason I don't have to put another t in front of here is because the eigenvector is what's going to make it Li, right? The eigenvector, which was negative 1/2, 1, 0, already takes care of that. This is a really important point, which I don't think I did a super great job of emphasizing during class. So again, if you're watching at home or here, wherever you're watching, when you have a repeated eigenvalue in the vector differential equations chapter, you don't have to stack a t in front of the second occurrence of that repeated solution. So if I have e to the negative t here, I don't have t e to the negative t here. The reason is just, as I said, I'll say it one more time, this vector is clearly not a multiple of this vector. So these two vectors are Li from one another already. I don't have to worry about it. In fact, if I really want to, I can test for linear independence of my three vector solutions by slamming them into the columns of a Wronskian matrix, and I guarantee you the determinant will be not 0, which means they are Li. Okay? Is everybody comfortable with that? Awesome. Okay, so that's a whole bunch of practice on a problem that wasn't on the review sheet, but I just thought it'd be good to go over it. So you see, just with this one matrix, we did a whole bunch of stuff. Okay. All right. If I give you a matrix that is non-defective, yeah, you'll always have n linearly independent eigenvectors, and you'll always be able to just build this general solution. And in terms of chapter 7, in terms of solving this system, I'm only going to give you non-defective matrices. The defective case is section 7.5, which I haven't covered. So you don't have to worry about that this week. But worry about that one next week. So it's actually kind of complicated, so it's just as well that we don't deal with it right now. All right, so now I'm going to go to the actual review sheet and start going through some of these problems. So let's look at problem number 1. It says, suppose that you have a matrix A at A cubed minus 2A squared plus 4A plus 5 times the identity matrix. Let's suppose that that is all equal to 0. This is just a quick little theoretical example. What I want to do is show that if lambda is an eigenvalue of A, of course, then lambda cubed minus 2 lambda squared plus 4 lambda plus 5 is equal to 0. This is actually a fairly famous property. It says that whatever equations a matrix satisfies, its eigenvalues will satisfy the same equation. It's a famous result that if you take, or when you take Math 307, you're going to see that in that class. Sorry, Joseph, would you mind sitting not in that row? I'm trying to get a video of this.
Oh.
I've got my camera set up.
Oh, sorry.
Sorry. No, you're good. You're good. No worries. Okay, so does everybody understand what the question is saying? Basically, it's saying we want to change the A's to lambdas. Okay. Does anybody have an idea? We don't have any specific matrix here. This is a more theoretical problem. Does anybody have any idea how to approach it? How do you want to start? Pardon?
AX equals lambda x.
Okay, except I use V usually, so I'm going to use V. So this is the key thing, guys. If anybody ever asks you, what's the important eigenvalue-eigenvector relationship, that's what you need to know. This is like the most important. This was the starting point for all of that theory of eigenvalues and eigenvectors. And look what this equation basically does for you. It takes capital A and turns it into a lambda, right? So you're almost seeing the very thing you're trying to show up here. You're sort of seeing that just in this basic little box right here. Okay, so it's not surprising that this would be the key tool for showing what I'm asking you up here. Does that make sense? Okay, so AV is equal to lambda V. Obviously, so for example, if I have A right here and I multiply it by V, I can change it to lambda times V. but we also have higher powers of A over here, right? So we might need to say something about A squared or A cubed. Does anybody want to say anything about what A squared V would be? You would want it to be lambda squared times V. You'd want to be able to take A squared and change it to lambda squared. And indeed, that is correct. Let me just show you, though, the math behind that. Okay, and this is the math I would want you to show me if I ask you this question. Basically, it's just A times V. But if I think of it as just the A and the V here first, that's already lambda V. So it's A times lambda V. And then the lambda is just a scalar. Remember that scalars can be put outside of the matrix. So we have lambda times AV. And so that gives me lambda times lambda V, which is lambda squared V. So at the end of this calculation, we have lambda squared V is equaling what we started with, which was A squared V, right? And then similarly, I'll just say similar, A cubed V is going to equal what? Right, lambda cubed V. Exactly. Okay, so we know how these powers of A behave when you apply them to V. They just turn the A into a lambda. So we're already halfway done with solving the problem now. We just have to go to the final last step. By the way, V is not just any old vector here, right? V is an eigenvector, right? So V is an eigenvector. In particular, it's not zero. That's important to remember. Eigenvectors cannot be zero. That's very important. I saw a couple of people do that on the quiz. I was asking for the, they were building the columns of the matrix S, and one person had like a column of zeros there. I was like, wait a minute, that doesn't quite work. The eigenvectors have to be not zero. Okay, so far so good? Great. So any ideas what I might want to do from there? Yeah, go ahead, buddy.
Replacing A's with lambdas.
And I want to replace them sort of in the whole thing now, right? In other words, I've done it kind of piece by piece just to sort of see how it works piece by piece, but now I've got to do the whole thing at once. Okay, so that's exactly right. Let's take A cubed, what was that? A cubed minus 2A squared plus 4A plus 5I. Let's apply the whole thing to V, right? That would be what I would want to do. Okay. Now, on the one hand, by the way, this big matrix that I just put in parentheses is actually the zero matrix. So I'm just going to emphasize, we already know that what we get is the zero matrix times V. What do we get when we take a matrix that is all zero and multiply it by a vector? You get what? The vector zero, right? By the way, notice how I'm being careful with my arrows. Some things have arrows on them and some don't. So try to follow my lead on that. It's important. I've been known to get out my red pen for those things. But be sure to put arrows on vectors and leave them off of scalars. Okay. So we got that. We know that this whole thing is the zero vector. On the other hand, what do we really have here? We have A cubed times V. Well, that turned out to be lambda cubed times V, right? So I'm just replacing A cubed V with lambda cubed V. Agreed? Then what do I have? I have minus, here's a 2, and then I have A squared applied to V. What was A squared applied to V equal to? Lambda squared V, very good. And I've already factored out to V, so I just have minus 2 lambda squared. Next I have 4 times AV. So what's that going to become? Just a lambda there, right? Okay. And then plus 5 times identity matrix times anything is just the same thing again. So that's just the V. Oh, look at that. I have some number here times my non-zero vector coming out to 0 vector. So what's that tell you about the scalar that you had to have had? Has to have been 0. Okay. So lambda cubed minus 2 lambda squared plus 4 lambda plus 5 is just 0. And that's the number 0 in this case. Okay, is that clear enough? Nice little problem. Okay, let's try another one. Let's try the next one on the sheet here. Number 2. By the way, as usual, this is just a review, very casual, no agenda, so if you guys have questions as we're going along, anything that's not clear, just fire them out. Okay.
Greg is stuck in the elevator, that's why he's not here.
What's happening?
Greg is stuck in the elevator.
In
It's been
this
an
building?
hour. Uh-huh.
In which
Yeah.
elevator?
Over there.
Has
And-
somebody called?
Yeah, he called the campus police and they're like fixing
I
it.
used
They've
that
been
button
helping him
and
for the last
it's
hour.
been on
They've been
fire.
helping him for the last hour.
Oh my gosh, and I was just in that elevator myself.
Really? It just got stuck
So
in
we
the
almost
hole.
didn't have a review session.
Well, I was thinking,
Oh my god.
Like that invited me after you. Yeah.
Right after me?
Yep.
I swear I didn't do anything.
I went and tried to like help
But
him.
the
And
arrow
they
was
called the
there,
campus
so it was
police.
There's nothing we can do, I guess.
Yeah.
So he's texting you though.
Yeah.
So he's alive and
Yeah.
he's just sitting there studying in the elevator. I don't know. Okay. So I know, I'm like, this is gonna be the evidence that I did something. So, I'm innocent. Okay, let's try problem number 2. What does it say? Suppose that we have a matrix A, and let's suppose we have 2 different lambdas, lambda 1 and lambda 2. And let's suppose they have corresponding eigenvectors, v1 and v2. So I'm not writing down all the words. Remember, if you want all the details of the question, just print it out from the web. Okay, so this is the usual setup. We've got eigenvalues, we've got corresponding eigenvectors. Here's what we want to show. And then this is probably just about the last proof that we'll do today. That v1 and v2, those 2 vectors, as a set, that is a linearly independent set. What this is saying is that if you have 2 different lambdas and you find eigenvectors for those lambdas, those eigenvectors are definitely Li. Where we get into trouble and why we sometimes get a defective matrix is when it's the same lambda that came up multiple times, didn't pull its weight, right? That's when we have a problem. What this is saying is you're never going to have a problem if you're working with distinct lambdas. In fact, we had a sort of a theorem, I believe I wrote down, that if you have a whole bunch of distinct lambdas with no repeats, then that matrix is already known to be not defective because each of the lambdas will produce an eigenvector, and now by this kind of reasoning, those eigenvectors are all Li. Here we're just asking you to do it for the case of 2 vectors, okay? So let's try and go through this. This is, I don't know, this is something that perhaps would be a little much for the midterm just because you're using the linear independence again, but we have a final exam in like a week, so it doesn't hurt to practice it now. So, and it's still beneficial. When you're showing that a set of abstract vectors is Li, the way you have to start that is with an assumption. Does anybody remember what it is? Exactly. Assume that you have a linear combination of those vectors that cancels out, right? And then what you want to do is you want to show that the constants are all 0. So the claim is that the C1 and the C2 are 0. This is what we have to be able to justify. Okay? But this is where we're starting from. Does anybody have a suggestion as to what I could do with this starting equation? multiply it by the matrix A. You know, I like that idea because then I'll get like AV1 and I'll get AV2, which of course is related to the lambdas, right? Eventually you've got to get the lambdas into this problem. So that's exactly what I'm going to do. I'm going to multiply by capital A. All right? So how's that going to look? Well, I'm going to get AC1V1 plus AC2V2 equals, what is A times 0 going to be? Always 0, right? Multiply by 0, you're definitely going to get 0. Okay, good. So we have that. And this, of course, can be now changed. The C1 is a constant. I can pull that out in front. And what am I left with? AV1. Let me just write that down. So AV1. So we have C1 times AV1 plus C2 times AV2. And that is all equal to 0. Okay. Now, what is A times V1 equal to? Lambda 1 times V1, right? Remember, AV equals lambda V. It's this equation in the box, right? We're using it again here. So this is C1 lambda 1 V1 plus C2 lambda 2 V2. That equals 0. Okay, so we have this equation. It's pretty important. I'm going to put it in a box. Okay? Everybody with me so far? So I started from here. I multiplied through by capital A and got myself down to here. This looks almost like the original equation. The only thing I've done is I've slipped a lambda 1 into the first piece and I've slipped a lambda 2 into the second piece. Right? So here's what I want to do next. Actually, I need more room. So I'll let you think about what I should do next while I erase for a second. Anybody have an idea? And by the way, the answer is the thing you don't want to do here is start subtracting things over. You're very happy to have these zeros on the right side, so you don't want to move that around. That's not really the answer. Any thoughts on what to do? Go ahead, Bobby.
So since lambda 1 is not equal to lambda 2, we can say that the only solution would be the C1, C2 is 0.
That's where we're headed. I don't think that's obvious just from this equation alone, though. I want to make it a little more clear that that is the case.
Well, maybe try to get rid of the vectors.
Say it one more time.
Get rid of the vectors somehow.
It'd be nice. So let me ask you this. If I've got, well, I like that idea. If I've got C1, V1, let's try and get rid of V1. If I've got C1, V1 right here, and I've got C1, lambda 1, V1 right here, just look at this and this. How could I make the V1 go away by using this and this?
Divide.
Multiply the top equation by lambda 1. That's absolutely right. Oh, I'm so excited that you saw that. That's exactly right. Okay. If I multiply the top equation, that's what I'm going to do, multiply by lambda 1, it's going to be C1 lambda 1 V1 plus C2 lambda 1 V2 equals 0. You see that? All right, Daniel, you said you wanted to get rid of a vector. I would like to get rid of V1. If I have this equation, and I have this equation, I have these two equations, how can I get rid of V1 now? Subtraction, exactly right. Subtract the boxes. And I'm just going to, I don't know which way you want to subtract them, but you're going to basically, the C1, the first terms are going to cancel completely. In other words, this is going to cancel that when you subtract.
Yeah.
You're literally like subtracting them vertically. And then the second term, you have a C2 in both places. You have a lambda 1 and then minus a lambda 2. I'll factor that. And then V2. and that is 0. Seeing where we're going with this? Is this 0? Is V2 0? No, because it's an eigenvector. It can't be 0. Is lambda 1 minus lambda 2 equal to 0? No, because lambda 1 does not equal lambda 2. So what do you conclude? C2 has to be the thing that is 0. Right? And now we're in real good shape, because as soon as C2 is 0, and even just going way back to the beginning, as soon as C2 is 0, now what do you have? You have a constant times